Here's the key for your reading notes in chapter 16.1 and 16.2. What I want you to do with your reading notes is go through and make sure that you make any changes, corrections. It's really important that you correct your work. With the pre-reading questions, obviously, those are just questions that are not from the book, but taken from things, wondering what you remember from previously, especially with you coming from multiple different junior highs. Regarding acids, we have covered multiple different acids before. We've talked about how an acid starts with the hydrogen. So that's what you're looking for. That's your basic definition of an acid. Two that we've used quite often in lab, which are two that I would expect you to know the formulas of right now, are H2SO4, which is sulfuric acid, and HCl. That was even on your final exam. Everyday things that are acidic, again, a lot of times people put things like orange juice, lemon juice, Coke, soda. Those would all be great examples. Here then is your definition of a base. Now again, this is a definition we have had before. It has the polyatomic hydroxide ion in it. And remember, your polyatomic is taken from the back of your periodic table, so you've used this OH ion a lot in the past. Again, pH scale, depending what biology class you had, depending which junior high you were at for your chemistry in 8th grade, you could have all kinds of different things you remember from that. But your pH scale goes from a 0 to 14 or from a 1 to 14, and regardless of what you start with, we're going to add a lot of information to that. Number 5, this is something we have had in a previous chapter. You can see it's in 18.3. This is something that you do need to know. 18.3 is when we went through our different reaction types, and we did have a reaction for acid-base reaction. The H comes from your acid. The OH is the hydroxide that comes from your base. When you put those two together, you have HOH, which is your water. And you may either write it, I'm writing it HOH because then you can see the hydrogen from your hydroxide, and you can see the OH from the base. So you are welcome to write it H2O. It's the exact same things. Okay, here are your first basic definitions, and I highlighted some of these in your very first notes. First definition being you have an acid and you have a base. An acid provides a hydrogen ion. This is something that I had you add to your notes, the proton donor. We will talk about that a little bit more later. Your base then, acids and bases are opposite. Your base is a proton acceptor. Again, that comes in with our second definition. And here's a big reminder here in yellow. By proton, we mean a hydrogen ion. Two models then, and I'll look to make sure the links are working. They're working on the desktop. I have to see if they might not work once they are linked. If they don't, I'll show them in class for you. These are two little short videos that help you go through these two historical models. The reason I want you to take a look, just a couple minutes on these historical models, is because the first one, the Arrhenius model, is your basic definition of an acid and base, just what we had up above. Your acid is your hydrogen ion. Your base is your hydroxide ion. Now, that was too basic. So what they did later, of course, as things progress in history, your next model is called the Bronsted-Lowry model, and it explains a lot more about what can be an acid and what can be a base. And our definition changes. Definition of an acid is known as a proton donor. Definition of a base, it is a proton acceptor. Remember that a proton, again, is a hydrogen ion. In this Bronsted-Lowry model, it's important to understand Bronsted-Lowry model works with conjugate acid bases, and those definitions will be down below. Okay, conjugate acid base pairs then, since these are part of the Bronsted-Lowry model, we'll be learning what a conjugate acid-base pair is. So here's your definition of conjugate acid-base pairs. Here again is a highlight in the definition from the book. They use the term proton. Remember, a single proton is your hydrogen ion. We're going to be doing a lot more of this practice in class, but in this Bronsted-Lowry model, when you're going through and identifying, here's our basic definition of an acid, because it starts with a hydrogen. Here, our definition of a base changes. But you have to accept right now that water is a base. When they change, on the opposite side of the equation, you have a conjugate acid, and you have what's called a conjugate base. So right now, just notice how they're acid-base on the left in the reactants, conjugate acid-base on the right in the products, and we'll be identifying those more later in class. Hydronium ion, you will hear this term a lot. Hydronium ion, and you see it in the equation up above, is your H3O with a positive charge. What this really is, it's your hydrogen ion that's a part of your acid. The H plus is never really found alone. It's always found as a part of the hydronium ion, but for ease of writing, we write H plus. And conjugate acid-base pairs, they are only one proton, or in other words, one hydrogen different. So when you look at the example that you took from 16.1 in the textbook, I have the answers in yellow. Number 1 and number 4 are your conjugate acid-base pairs. Reason is, when you go from H2O to H3O, it is only one hydrogen different. Number 4, going from its acetic acid to the acetate ion, you have lost one hydrogen. So it doesn't matter if you've gained a hydrogen like in number 1 or lost a hydrogen like in number 2, they are one hydrogen different. Number 2 and number 3 are not conjugate acid-base pairs because when you look at number 2, you have lost a nitrogen and oxygen, so that doesn't count. And in number 3, you've lost hydrogens, but you have lost 2 hydrogens. So again, definition of conjugate acid-base pair, when you look up here to number 3, or when you look up, lost the definition, number 3 right here, they are only one proton different. Acid strength, again, this is just the beginning of going through what a strong and what a weak acid is. What I want you to understand is that the reaction is reversible. You've not really seen that term before, and you've not seen this double arrow before. So when you see this double arrow, that means you have a reversible reaction. You have your reactants going to your products, and you have some of your products moving towards the left side of the equation, and so those two are going back and forth. It's an equilibrium type reaction. What this HA means, this is the general symbol for an acid, because here's your hydrogen, and that's the hydrogen that's being donated. Okay, with your definitions of strong and weak acids, you should have these definitions from the textbook. You can take a look at those. Diprotic is a term the book will use. You will see it some, and I'll notice it's when you have a series of more than one hydrogen that can be donated. Also, the term oxyacid, I won't use it that much in class, but you'll see it quite a bit in the textbook, and you'll see it some on the OWL program. One thing to understand is that when you're talking about an acid, strong and weak are different than concentrated and dilute. Concentrated and dilute refer back to molarity, which is what we covered in the previous unit. So strong and weak characterize the strength of an acid with how much it can donate a hydrogen or a proton, but dilute and concentrated refer to how much water is also in them. Now for strong and weak acids, there's a whole bunch of weak acids. I gave you just a couple for examples. What you need to do is, I have it highlighted here. These are your 4 strong acids, and you need to simply memorize these formulas. HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid, and HClO4 is one we don't see very often. We don't use that in class. That one's called perchloric acid. Amphoteric is a term I've used in class before. It means that water is our main amphoteric substance, can act as both an acid and a base. In other words, it can give up a hydrogen or can also gain a hydrogen. Ion product constant, again, you see this equation. This is the definition of what the equation is with the Kw. And these are your definitions of acid, base, and neutral in comparison to the concentration. Remember, when you have that square bracket around your ion, that means the molarity or the concentration. Here are the 4 equations that we're using. You already have those in your notes. These are all, 2 L's in all. These are all a part of the pH wheel. Read the rules about sig figs. We won't be focusing on that in class, but again, just don't get carried away. There's 3 ways you can measure pH, and we've already done 2 of them in class. We've used pH paper the first day. We also used our pH meters the first day. We'll use both of those again. And we will be using pH indicators in labs later this week. Since a lot of you often go down and visit University of Illinois, or you might have parents that went to University of Illinois or siblings, there's a building at the campus of University of Illinois that was built by this person whose name is Arnold Beckman. And there's a really neat part in the book about him. If you didn't read it, read about him. And if you visit campus sometime, take a look. This gentleman has donated all kinds of money. He made pH meters, and this gentleman has donated all kinds of money to many different education organizations. And so when you go to U of I, there's a Beckman Institute that you should check out sometime. And there's a picture of it. Okay, keep listening, because there's one more thing you need to do. If you are in second, or if you are in third or fourth period, put a big star at the end of your notes. If you are in sixth or seventh period, put a big heart at the end of your notes. And if you are in eighth period, put 2 big stars at the end of your notes. And that's all.